All right, everyone, welcome to episode 2 of Catherine has a Wednesday afternoon free and decides to do some fun math. So in this episode, we are going to be calculating the value of e to 5 decimal places. First off, we are going to have a claim. This is a little lemma that will become important later. The limit, as n goes to infinity, of 1 over n to the k times n choose k equals 1 over k factorial. The proof of this is pretty straightforward. I'm going to start out by writing the algebraic definition of the choose function. Since I know that n is going to be greater than k, since otherwise the choose function doesn't make any sense, I can cancel out those remaining k terms from the top and the bottom. Then I'm going to take that 1 over n to the kth power from the beginning. I know that there are k terms on the top of the fraction, so I'm going to assign each of those k terms in the top of my fraction a 1 over n. This first one is going to cancel to 1, and everywhere else I'm going to distribute. So I have a 1 minus 1 over n, 1 minus something over n, all the way up to k plus 1 over n. Then when I take the limit, all of these something over n's is going to go to 0, and I'm left with 1 over k factorial. Next step, I'm going to prove that e to the power of x equals the sum, as k equals 0 to infinity, of x to the k over x factorial. This first proof, I'm going to start with the definition. This is why it's called Euler's number, that Euler, who was an accountant finance guy back in a long time ago, discovered this formula for the number. He found the constant and used it in his stuff. So I don't know if you're perhaps an accountant, maybe this looks familiar, perhaps these things are completely irrelevant by this 200 years later point. But that is, in any event, the definition of e to the x. Next, I'm going to use the binomial theorem. The binomial theorem comes in handy super often. I used it in the calculation of pi as well, to show that 1 plus x over n to the nth power is actually just going to be the sum, as k equals 0 to infinity, of n choose k, k to the x over n to the k. Now this is where lemma, which I called 1 because mathematicians are quite unimaginative that way, I'm going to apply that to this sum. Since I have there a n choose k over n to the k power, and I'm going to infinity, I can show that the limit equals the sum of x to the k over k factorial. Since I know that limit equals e to the x, and that the limit also equals the sum, by the transitive power of addition, or of the equal sign, I can say that that sum equals e to the x. After all, equals is indeed an equivalence relation. Now I have my favorite part. I can take this formula, e to the x equals the sum of x to the k all over k factorial. I'm looking for e to the first power, just the value of e, without any fancy frills. So I'm going to plug in 1 for that x. And then I have a lovely book called Tables of Integrals and Mathematical Data that I found in Taos, actually. And it is a lovely book. It has everything one could possibly need to know, including a list of decimal values for 1 over factorials from 0 all the way up to, I think it has 12. So I used that book and also a computer program called Desmos to calculate this, and I was really surprised actually. This converged remarkably fast. With only, 10 terms, so up to k equals 9, we have 2.71828, which is 5 decimals of accuracy, which is pretty good considering that the actual value of e is 2.71828, 1828, 459045, etc., etc. And there you have it. Now, here's my one hesitation. This part right here, where I use the binomial theorem. To really be complete about this, I kind of feel like I should provide a proof of the binomial theorem if I'm going to use the binomial theorem. And the proof of the binomial theorem is really cool, and maybe when I have another Wednesday afternoon when I'm not doing anything, we can prove that on this wonderful whiteboard in the library. But since I don't want to do that right now, we're instead going to prove it with induction. One, because induction is awesome. In discrete mathematics right now, I'm teaching people how to use induction, and this is a really cool way to show them, I guess, a quote-unquote real-life application of the inductive process. Induction, or I should say the principle of mathematical induction, is actually an axiom. It says that if you can prove something for some base case, in this case you see I used x equals 0. If it works for some base case, and you can show that if it works for some value n, then it works for some n plus 1, then you can say that it works for all values of n. A good analogy to this is what we call the domino effect. That base case, you can prove that you hit that first domino. You have to make sure that that first domino is indeed going to be knocked over. And then if you can prove that for every domino you knock over, the one after it is also going to fall over, then you can say with confidence that the entire line of dominoes is going to be knocked over. So here it is, E equals the sum by induction. And then from here, we'll jump back to this section where I still use that important lemma. That lemma comes in the exact same place to show that that sum equals e to the x, where I can then plug in my values and find the value of e.